those sections where people say, well, how does this fit in with all the other stuff we've been doing? Hang in there. It does. It fits in really well. We've got inverse relations and functions to talk about today. And to find the inverse of a relation or a function is what we're doing. On Wednesday, Thursday, and Friday of last week, we really talked about concepts that you need to be an educated consumer. Things that you have to know, about coupons and discounts and all that kind of stuff. And this is definitely a headline that you could see in any local paper, as over the years, civil servants have said, you know what, I take a break on my income. I got to raise taxes on everybody else, and they're saying, why are you raising taxes when you make so much money? So you know what I'll do? I'll let them cut my income a little bit. So this says, what is wrong with the headline and why? And what headline would you have written? Mayor's salary restored. At last night's meeting, the town council approved a 20% increase in the mayor's salary. This follows last year's 20% decrease, and the mayor's comment was blah, blah, blah. Well, here's the problem with that. If the mayor took a 20% decrease, how much of his income did he take home? 0.8. So now it says what they decided to do was this year say, okay, now we can afford it. We're going to go ahead and we're going to give you that amount, but we're going to increase it another 20%. Well, if they're giving him this amount and another 20%, they're giving 100% of this plus another 20. And that's going to be 1.20. And we talked about how even if we don't know what that income was, we certainly could do this math of 1.2 times 0.8 to see how close this is to what the mayor was making before. And it comes out to this. So I just grabbed my hand calculator, Google Meters there, and just punched in 1.2 times 0.8. Is that 100% of what he was making? No. Well, how did that work? I mean, they took 20% away and then they gave 20% back. Well, because they gave 20% back on a lower amount. That's how. So, if we were writing the headline, I would hope we would say something like, mayor's salary almost restored. Knowing, yeah, it's pretty close, but it's not what they were making when they decided to take the pay cut because of bad times, recession, whatever it might be. So the math is what helps you understand that. When you want to raise, you have to think about it. Are they going to finagle the numbers so that you're really not making much in addition to what you were making before? You have to understand those things, and you have to check them. You do. There's been, a couple of big cases, but the most recent one of somebody that had a ton of money who just totally got shredded of that money. You guys probably know who Billy Joel is. Your folks probably listen to Billy Joel's music. Billy Joel was a big one. He's got a lot of money. Okay. They do want to talk to me. Hi, Mrs. Cedarholm. Yes. Oh, okay. Thank you. Bye-bye. Riley, your dad is here to pick you up. I don't know if they put a pass in there for you or not, but you can just stop at the attendance office. All right, anyway. So Billy Joel, he's got a long story, a very tragic life. His first fiance died in a car accident right before they were going to get married, and he had a brother-in-law who was an accountant. And to help out the accountant, and keep it kind of in the family, he said, well, why don't you be my accountant and take care of all of my money? And several years later, he gets a call that, his checks are bouncing all over the place and he doesn't have any money in the bank. And he goes to check it out, and his brother-in-law had taken all of his money and was off on an island somewhere where they couldn't find him. Now hopefully that's a problem we can all have, right? We have a ton of money and somebody rips us off. That's a really bad problem to have. But you want to make sure that what you're supposed to have is staying yours. And you can't just hand things over to people and expect them to do what's right for you. So that's a big piece of this. But to understand how all of this works forwards and backwards, we have to know what an inverse is. And an inverse is that backwards process, that undoing of something. So if a relation pairs element A of its domain to element B of its range, the inverse relation undoes that. So it pairs B with A. It switches that back around. So A to B becomes B to A. Oops. I have a spare packet. Could you not find yours? It's hard to take notes when you don't have a packet. Yeah. Anybody else? Alrighty. So, if we have a graph and they tell us, well, we want you to find the graph of the inverse, all we have to do is take the x's and y's and switch them. That's what we do. So A to B maps to B to A. You reverse those two. You did this in geometry, and it actually is a reflection over the line y equals x. And y equals x is the perfect diagonal through first and third quadrant. Now, if both the relation and its inverse are functions, then they're called inverse functions. It could just be called an inverse, but it is really nice if they are both functions, because then we can call it inverse functions. So, anybody need a reminder of what a function is? Functions, to be a function, for every input, there is exactly one output. You put one number into the formula, and you get one number out. Which at this point, you'd probably be saying, well, when don't you? I mean, we've done a lot of them. And when is this going to happen? Actually, on today's stuff, it starts happening. We start seeing that there are some where you put one number in, but you actually get two numbers kicked back out. And that would not be a function. So for every input, there's exactly one output. Anybody need more time? All right, away we go. So here's our essential understanding. The inverse of a function may or may not be a function. We have to check them both. We know we can use the vertical line test to check and see whether or not something is a function, but to do that you have to graph it. So that's why I gave you the definition. For every input there's exactly one output. This diagram shows a relation, R, which just happens to be a function. So that means for every input there's one output. You put in a 1.2, you get a 1. Yeah, that's one number. You put in a 1.4 and you get a 1. Still, just one number. Put a 1.6 in and you get a 2. Yep, that's one number. 1.9 and you get a 2. One number. Then I look at the other one and I realize that's not going to be a function. You put a 1 in, you get both 1.2 and 1.4. That's two outputs. That one's not a function. So the diagram shows a relation, R, shows its inverse if we reverse that, and its inverse is not a function. The range of the relation becomes the domain of the inverse. So domain is the x's, and range is the y's, and those two things flip. So that's how we need to think of our inverses. Problem 1 says, let's just find the inverse of a relation. What is the inverse of relation S? Well, they gave us a table, So we're going to give them a table back. And we're going to label this one S to the -1. Because unfortunately, that's the symbolism we use for inverses. It looks like you're raising it to the -1 power, but that's an inverse. All I have to do is switch the x's and the y's. So these y's now go here, and these x's go here. We just made an inverse, switching the x's and the y's. So it says, let's take a look at these graphs, huh? Let's graph S. So we're just going to go back to this green table and graph it, and they've got those points there. And then we found the inverse, and let's graph those points. -1, 0, 0, 2, 2, 3, and I am just guessing here because all those lines are gone, and 3, 4. So the original and the inverse. Now, like I said, it should look like it's been a reflection of the line y equals x. And the line y equals x is the perfect diagonal through first and third quadrant. And there it is. Now, would it be a function? Well, we could use the vertical line test. They're not asking us about that yet. So let's just keep going until they do. 1a says, how about t and its inverse? Well, looks like they're making a sideways table this time. So we'll make a sideways table too. But all we have to remember is the x's become the y's and the y's become the x's. Like so. So let's put the original on here. Let me see if I can get those graphs to darken up at all. That's better. So the first one had the points 0, -5, 1, -4, 2, -3, 3, -3. I'm going to go ahead and graph the inverse on a different color, but on the exact same set of axes here. So that one would be -5, 0, -4, 1, -3, 2, and -3, 3. And again, you can see how that would definitely be a reflection over the line y equals x. So now they're asking us, for number 1, what are the graphs of t and its inverse? And then for b, is it a function, the original? Well, the original one was in black. And yep, I can draw a vertical line anywhere on those points and only hit in one spot. So yes, t is a function. Is t inverse a function? Nope. Right here at x equals -3, if I drew a vertical line, it would hit it in 2 spots. Not a function. Explain? Well, it fails the vertical line test. So if we graph them, we should just use the vertical line test. It's the fastest way to talk about what's going on. So the graphs of the original and its inverse are, like I mentioned before, reflections in the line y equals x. To describe an equation for the inverse of a relation of a function, well, now things are going to change. So they're saying, now we're not going to have you graph it. What we want you to do is write it. We're going to give you an equation, and you have to write the inverse. There's only two basic steps. We switch the x and the y, and we solve for y. Two steps. Switch the x and the y, and solve for y. So step one, switch the x and the y. X's become the y's, and y's become the x's. Thank you. Once we're done with that, it's going to look really weird because it's going to say x equals blah, blah, blah. We know that's not right. We know we always want y equals blah, blah, blah. So we're going to have to solve for y, get y by itself. And then if it says graph, we graph. If it doesn't, we say, here's the inverse. Away we go. So two steps. Switch the x and the y and solve for y. Problem two, finding an equation for the inverse. Okay, two steps. Switch the x and the y and solve for y. What is the inverse of the relation described by y equals x squared minus 1? Keep thinking in those two steps. Switch the x and the y. That wasn't too hard. That first step should always be easy. All we do is make the x a y and the y an x. But the second one can sometimes take a little bit of math because we have to solve for y. So if I want this alone, I'd have to add 1 to both sides. And then I'd have to figure out how to get rid of squaring something. Yes, square root. And now I need everybody to remember, when we physically write a square root symbol down, we have to put plus and minus. Well, you know what question they're going to ask us about that. They're going to say, is the inverse a function? And we better say no. Because every answer we get here is going to have two answers, a positive and a negative. But they're not asking us yet, so let's hang in there. Got it 2 says, what's the inverse of y equals 2x plus 8? You're already doing it, but tell me what step 1 is. Flip them, flop them. Then how do we solve to get y by itself? Subtract 8. Then what? Divide everything by 2. And we probably should put it in slope-intercept form just in case they have us graph, because they're going to want to see, do we understand that we're reflecting over the line, y equals x. So remember, this is a 1x. 1 divided by 2 would be 1/2 x. Negative 8 divided by 2 would be negative 4. So there's our inverse. Now that one's a function. There's no plus or minus there. So I started thinking, can I know in advance if an equation is going to have an inverse that's a function? Yeah. Am I going to have to take an even root? If I have to take an even root to solve it, then the answer is no. We're going to get a plus and a minus for it. Alrighty, so this one says, let's take a look at the graphs. And to do that, we actually need to see the graphs. There we go. Alrighty, so first one, y equals x squared minus 1. Okay, well, back in exponential, you learned that x squared is a great big parabola, and we did those again this year in Algebra 2. But this big parabola needs to move down 1. So let's remember what y equals x squared looks like, because that's our parent. Nice little graph. Using -3, -2, -1, 0, 1, 2, and 3. And all we have to do is square those numbers. Negative 3 squared is 9, negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. But I have to move all of those points 1 unit up for y, or sorry, 1 unit down. I forgot it was a minus 1 instead of a plus 1. So if you move something down 1, are the x's or the y's changing? The y's. So let's go ahead and make this our y minus 1 column and just subtract 1 unit from each of these y's. So when we graph it, we'll just ignore the middle column. Negative 3, 8. Negative 2, 3. Negative 1, 0. 0, negative 1. 1, 0. 2, 3. And 3, 8. And a nice, well, as best you can, nice smooth curve. Nice little parabola right there. Now, if you happen to have a different color, maybe use the different color if you have a pen with you or something like that to do the inverse. Now, here's the interesting thing about this one. After we learn section 6.8, we're going to be able to graph that super fast. But this is a good point for us to say, okay, what does the graph of square root of x plus 1 look like? Well, let's see. I know I can't take the square root of negatives, because that would be imaginary, and we're not graphing on an imaginary plane. So the smallest number I'll be able to put in there will be negative 1, because negative 1 plus 1 is 0, and the square root of 0 is 0. And then I'd probably want to see some numbers, going to the right. So I started thinking, well, if I put a 1 in there, then I have to know what the square root of 2 is. I don't want to know what the square root of 2 is. If I put a 2 in there, the square root of 3. No, I don't want to do that one either. How about if I put a 3 in there? Ooh, I like that one. 3 plus 1 is 4. And the square root of that will be 2. Oops, dropping things. But, come on, blue. There. Ornery smart word. We have the plus or minus in front, so plus or minus 2. All right, for 4, it'd be the square root of 5. Don't want to do that one. 5, square root of 6. Don't want to do that one. 6, square root of 7. Don't want to do that one. 7, square root of 8. Don't want to do that one. 8, square root of 9. Ooh, I like that one. So we picked numbers that would work nicely because of the square root. So we have negative 1, 0 is kind of our little starting place. And then if we go to 3, we have to go both up and down 2 and make a dot. And if we go out to 8, we have to go up and down 3 and connect that up into a smooth curve. Like so. So with this one, the black one that I have up there, that's a function. That passes the vertical line test. But we can see, oh boy, is that blue one not going to pass that vertical line test at all. So the red one, definitely a function. But the blue one, And we know the culprit. The culprit was that plus or minus. So what up here in the red one, everybody, before we flip the page, what up here should tell me the inverse of this is not going to be a function? Yeah, squared, power of 2. We're going to have to take a square root of both sides, which means a plus and minus. So we can tell beforehand when we look at those. All right, this one says, how about the other one we did? Y equals 2x plus 8, and then it's inverse. Well, that one's much easier to graph if you remember how. Do you remember how to graph in slope-intercept form? Some are shaking their heads no, others are like, yes, I've got this. Mx plus b. So think about almost everything in math is alphabetical. So b would definitely come before m. We start where the y-intercept is 8, way up there. And then we use the slope to figure out where to go from there. John, take some notes. 2, that's not a fraction. For slope, we always want a fraction. What should we make it? 2 over 1. Remember, slap that 1 down there. So we're going to have to go up 2 and to the right 1. And now we're already off the grid. So let's use the slope backwards. Let's go left 1 and down 2 a couple of times. I don't know about you, I'm pretty bad at drawing a straight line if I don't have something to aim at. Now I can connect those up nicely. Or at least get reasonably close. And I'm going to switch colors. And we already wrote the inverse to this one, just to remind everybody. We had 1/2 x minus 4 equals y. So where would this graph start? Where's that starting point? 0, -4. And then how do I move from that spot? Use that slope up 1 and over 2. Again, I'm going to do that a couple of times here. And backwards. Does that first line, the black line, does that pass the vertical line test? So that was a function. How about the red one? Does that pass the vertical line test? They both do. So this is an instance where, yeah, this was a function and its inverse is a function. So like we discussed before, if you see an equation that has an x squared, an x to the 4th, an x to the 6th, an x to the 8th, any kind of even power, you're going to know, no, the inverse is not going to be a function. But the rest of it should all work out pretty nice. So down here, we're going to learn a new notation. It's not new math, and all it does is says, well, if you're not here to explain this to somebody, how is somebody going to know that the inverse of y equals 2x plus 8 is y equals 1/2 x minus 4? Well, they wouldn't, unless we write it like this. F to the -1 means the inverse function. Now, you're going to see it like that, but most of the time, books will do this again. So they're using function notation, and they're showing the inverse of this function. That's what the red one is. It's the inverse. So somebody that knows a little bit of math will be able to look at it and say, oh, now I know what they were doing. They were finding inverses. We don't. And a good explanation for why is not coming to me right now. but it typically, Matt, is just because it's functions, you know, and if we're talking about functions, then we've got our f of x, h of x, g of x, all that kind of stuff that we're using for it. The inverse of a function f is denoted by f inverse, and you read that as the inverse of f, or as f inverse. And the notation f of x, remember, is used for functions, but the relation of the inverse may or may not be a function. So here's what they're saying. This was our original up here in the black. If we call this f of x, even if the red one doesn't work out to be a function, it's okay to call it f inverse of x. It's just a way of us saying this was the original and this was the inverse. So it doesn't have to be a function to write the inverse. Alrighty, let's go after some that are a little tougher. Consider the function f of x equals the square root of x minus 2. What are the domain and the range? Well, we already talked about domain for these. Last week we said we can't do negatives, so x minus 2 will have to be greater than or equal to 0. Because we can find the square root of 0. It's 0. Well, that's easy enough to solve. Let's add 2. Now this one was named f of x, so we'll put domain and then we'll put a little subscript there of an f, and it was x is greater than or equal to 2. But to figure out the range, we actually kind of have to know what it looks like, visualize what's going on. So the range of f, capital R of f. And I'm going to flat out tell you, since we're going to learn about this in the next section, positive square root graphs look like that. And what we just found by putting that 2 as our lowest x was that our first y value here is going to be 0. Because we put a 2 into the square root of x minus 2. 2 minus 2 is 0, and the square root of 0 is 0. So with this one, because it's assumed there's a positive 1 in front, it's going to curve upward. So our range here, well, the lowest y value we'll ever have is 0. Y is going to be greater than or equal to 0. Easy way to get that, whatever you have for your cutoff for the domain, put it up in here and see what's the smallest number I'm going to get for my y's. And then you can go from there. So B says, what is the inverse of f? Well, there's 2 steps to writing an inverse. What's the first one? Oh, well, there's no y. That wasn't very nice of them. They're saying we need to remember that f of x is just fancy notation for y. That's all it is. So the first thing we would do is we would write it out with a y instead of an f of x. And then, like you said, we got to swap them. So we're going to have to swap those out. X becomes y and y becomes x. But now we have to solve for y. How do you get rid of square root? You square it. We have to square both sides. There, now we have access to that y. So how do we get rid of the minus 2? We add 2 to both sides, yeah. Now, it said right here what we have to name it. We can't leave this one y. What is f inverse, the inverse of x? So now we'll put our little f to the negative 1 down there to make it look fancy. And if you want to, you could put f to the negative 1 of x. All right, that was A and B. C. What are the domain and range of the inverse? Oh man, that would mean I'd have to grab my graphing calculator and graph x squared plus 2 and figure out what's the lowest x, what's the lowest y, and all that. No, because here's what we know. What's step 1, the inverses? Switch the x and the y. The domain becomes the range, and the range becomes the domain. That way we don't have to see them. Domain becomes the range, and range becomes the domain. The x's and the y's swap. Was that inverse a function? Take a look at our inverse. Did we have any plus or minus in here when we solved it? It's a function. So you're explained because we don't want to graph it. I mean, we could. Does everybody remember what y equals x squared plus 2 looks like? Draw it in the air for me in front of you, please. What's it look like? Okay, big parabola, but where does it start? Up 2, yes, because it's got the plus 2 in there. Better because we didn't graph this one to say for every input there is exactly one output. Definitely. Because we don't want to have to graph it. Like I said, not the hardest thing to graph in the world, but we don't want to have to graph it. Alrighty, more of you and less of me, even though you guys are looking really tired today. Well, first things first. We know the 2 steps to an inverse, right? What is this missing that we're going to need? What's step 1 of inverses? Yeah, it needs a y. So let's do that, make our lives a little bit easier. Domain and range of G, so domain and range of the original. Well, there's nothing funky about that one. If we graphed that, what would it look like? They're betting we don't see it. If we graph this, what will it look like? It's a line. Does everybody see they just put it up there backwards to confuse us? Well, let's make it y equals mx plus b. Apparently confusing us worked a little bit early in the morning, right? So if it's a line, didn't we draw some lines earlier? Were they functions? They were. And they had arrows on the ends, didn't they? What do arrows mean? Ooh, they go forever. Domain and range is all real numbers. Remember, you can use the fancy R with the extra line on it for all real numbers. Well, now they want the inverse. And that's for part B. So first step, switch the x and the y. Then what? Step 1 is switch the x and the y. Yep, we got to get the y by itself. So we subtract 6 and divide everything by -4. Remember, there's a little imaginary 1 here. Now it's almost done. What's missing from it to tell somebody that just looks at it right away, this is an inverse? What's missing? Yeah, a little notation thing. But this one is going to be g inverse of x because they called the original function g. There we go. So C says, don't let us trick you. What's the domain and range of the inverse? Exactly. Because you just take the domain and the range of the original and you flip them over. You swap them. And the last question they have for us. When we wrote this inverse, is it a function? Well, the only way we'd have to say no is if there's a plus or minus in this somewhere. Did we have a plus or minus in front of anything? It's a function. And like I said, without graphing it, we just want to use the definition. So for every input, there is exactly one output. Because graphically, we could talk about the vertical line test, but they didn't give us any graph paper for these. They said, hey, just go after it from what you see. We're already done. How did that happen? So, questions about anything that we've talked about with inverses today? Because like I said, some of you are looking a little sleepy today. All right. Well, yep. Good stopping point. There it is. The light's on here. Maybe that'll help you wake up a little bit. So section 6-7, day 1, page 410. You got 9 through 19 odd, 75 to 77, and 85 to 88. And I should check and see if you would want graph paper for this. Oh,